So in this section, in the following videos, we're going to review the method of partial fractions and use it to solve integrals. So the method of partial fractions was a method to rewrite a rational function like the one given here as the sum of two fractions with simpler denominators. The key point is that, I'm going to use this example to explain what's happening. The key point is that this polynomial that I started with can actually be factored, right? The denominator can be factored, like x minus 3, x plus 2. So the key point is to think that I could have gotten this expression with this numerator by combining two expressions with these two denominators. When I added them to get the common denominator, I would get this expression over here. So who are my two terms that I had here in order to that when I added them, I got 9x minus 7. So that's the logic here. I could have, can we find a way to express 9x minus 7 over x squared minus x minus 6 as the sum of two terms, one of them with the denominator x minus 3, the other one with the denominator x plus 2. So if we can do that, I would have, I'm going to write it like this. If we can do that, I would have had to combine these two terms. I would have multiplied a times the denominator x plus 2, right? I'm trying to say if I combine these terms in the same denominator, I would have to multiply the b times x minus 3. That way, I would have the combined denominator of the product x minus 3 times x plus 2. And now, just since these two expressions have the same denominator, we're going to assume we're at a divisor where this is not 0. I can just ignore them and say what I really need is the top to be this. So now we expand this, and I get bx minus 3b. And now the key point is to say, well, I have a polynomial on the left of degree 1, a polynomial on the right of degree 1. If they're going to be equal as polynomials, the coefficients of the x must match, and the linear terms must match. What do I mean by that? That a plus b, let me change this, should be 9 and 2a minus 3b should be the negative 7. Okay, so then I really end up having a system of equations where a plus b should be 9 and 2a minus 3b should be the negative 7. So now my problem changes to just solving this system of equations over here. A plus b equals 9 and 2a minus 3b equals negative 7. So can I solve that system? Sure. We have several ways to solve it. I can do substitution or elimination. I prefer to use elimination whenever I can. So I'm going to do that. To do it, I'm going to multiply the first equation by let's multiply by a negative 2. So if I multiply the first one by negative 2, I'm going to get negative 2, negative 2a minus 2b equals negative 18. I copy the second equation as it is, because if I do that, now I'm going to cancel the a's, right? So when you add these two equations, the a's cancel, you get negative 5b equals negative 25, which gives us that b is a positive 5. So going back to any of the original equations, I can grab this one, for example, and I have that a plus 5 now, since I know that b is 5. A plus 5 is 9, which gives me that a is 4. So there we go. So we found it. We found that our solution that we wanted, let me write this down here. Let's get some space. So finally, we got that 9x minus 7 over x squared minus x minus 6 is the same as a, which was 4. I'm copying it from here. It's important to see which one I use over x minus 3. So 4 is the a, which was the factor x minus 3, and the b was 5, was over the factor x plus 2. Okay. Now, how are we going to use this in calculus? Well, simple. Let me copy this one. This is what I did. So now if I'm asked to solve an integral that has exactly this as the integrand, this is exactly the problem I did in the past slide, then I can say, oh, if I use the method of partial fractions, I'm going to say, using the partial fractions method, we get that that integral is the same as solving this integral. Oops, I didn't get it. It didn't paste. There it is. Okay, I got it twice now. Okay. So in order to solve the integral this is much easier. Because each one of these is, the first one is natural log. I do a u substitution where u is x minus 3. It's simple. The first one is 4 times the natural log of x minus 3. The second one is 5 times the natural log absolute value of x plus 2. So that's how we use the method of partial fractions to do these problems. Now, in a real situation, it's going to give in to you like this, right? You use the partial fractions, we're going to give you the integrand as a rational function, and we have to decide if it's a partial fraction is a good method to solve it. So I skipped this slide very quickly. So what do we need to do this? Well, we're trying to work integrand. We want to write a function that has a denominator on the top and in the bottom. What do we need? We need the degree of the top to be smaller than the degree of the bottom. So it needs to be a proper fraction. If not, we would divide first and work with the remainder. So we first have to check that our numerator has a smaller power than the denominator. The other thing that's important is we're assuming that we know how to factor the denominator. This is not always easy. It's not always possible. In theory, it works. Every polynomial of degree n will have, you can write it out, something we saw in pre-calculus. You can write it out as a factors, a list of factors of multiplicities. Some of those might have, if you cannot reduce a quadratic factor, it stays in the factorization because we don't want to introduce complex solutions, so complex zeros. But in theory, we can always do that and find either quadratic irreducible factors or linear factors, possibly with multiplicities. And then when we get the factorization, then we use what we just learned before. It's called the method of undetermined coefficients. The coefficients are the a and the b in my example, and we get a system of linear equations, and we should be able to solve it. In my example, I had only 2. I had 2 equations with 2 variables. If we have more, it might get complicated, right? We might have, so in practice, in the Calculus 2 class, we never ask very complicated things. It might have degree 2, degree 3 if we can factor. Or sometimes we give students the factors in the denominator. Okay, so on this one, let's use this again in another example. So on this one, I could factor the denominator as x plus 1 and x plus 5. So let's work. I'm going to find the factorization. I'm not going to copy the integral. We're going to find the factorization. Okay, so I'm going to write not the integral, but just the negative 2x plus 6 divided by x squared plus 6x plus 5 will be, I wanted like 2 terms. One of them will have denominator x plus 1. The other one will have denominator x plus 5. Because those are the factors of my denominator. Okay? So what I'm writing here is that I'm going to have negative 2x plus 6 as x plus 1, denominator as x plus 1 times x plus 5. And over here, I'm going to write it like, when I combine them, I get a times x plus 5. I will need to multiply by the other denominator in order to have them combined under a simple denominator, under one single denominator. So I'm writing it like this to be clear that since both sides have the same denominator, we only look at the numerators. Okay. So then I get the negative 2x plus 6 should be equal to, I get ax plus 5a plus bx plus b. And now factor the x's to see who would be the coefficient of x, a plus b times x, and my linear term, or my constant term, sorry, is 5a plus b. So same as before, now my a plus b should be negative 2, and my 5a plus b should be 6. So those are my system of equations with two variables. So let's write those over here. The system I got is that negative, let me write it like this. Let me write a plus b was negative 2, and 5a plus b was positive 6. So I need to figure out a way to solve this system. Since I have a b by itself on both equations, I can say multiply the first one by negative 1. So I get negative a minus b equals a positive 2, because if I add that equation to the second one, when I add them, the b's cancel, and I get 4a equals to 8, which gives me that a is 2. Sorry, a is 2. Yeah, that's right. So we got the value of 8, and now all I have to do is find the value of b, and I can get, again, any of the equations. Just grab the first one. So instead of a, I could put 2 plus b should be negative 2, so b is really negative 4. So there you go. Once we have this, we can just rewrite my integrand like the sum of two fractions that I can easily solve. So the integral I was asked to find of negative 2x plus 6 over x squared plus 6x plus 5 can be rewritten like the integral of a, which was 2, over the denominator x plus 1, plus b, which is a 4, so put negative 4, over the denominator x plus 5. And I skipped a step last time, so if you want to, I would write now, let me write this time like this is really, you're splitting this up like 2 times the integral of 1 over x plus 1, and I'm going to put a negative 4 times the integral of 1 over x plus 5. Okay, and in each one of these, I'm doing a u substitution, where u is x plus 1, so du is dx, and you have 1 over u du. Right, so in each of these cases, it's a simple integral to form 1 over u du, so the integral of that is natural log of u. Right, so that's what I didn't write. You should have experience with those by now. So then that's why this becomes 2 times the natural log of absolute value of x plus 1. This becomes 4 times the natural log of absolute value of x plus 5. And the other constant. Okay, so this is my first video for partial fractions.